With respect to object lifecycle, we can also talk about possibilities of allocating objects dynamically. So dynamic versus static allocation in general, the idea behind it is that this is a string, and each string that we try to create, including an array of 10 strings, we were creating these objects, and the size of 10 strings, the size of single string here and here, is all well known to the compiler. Every time that then when we know exactly the sizes of memory allocation that we're attempting here, we call it static memory allocation. In our case is a local memory allocation also, because these are local variables of function main. So, however, it's possible to allocate objects dynamically. So some examples right here. For instance, we can create a new integer dynamically. So the integer is created at runtime. The integer is allocated. So basically, the idea behind here is this is just purely demonstration idea. So an integer is allocated in memory dynamically in the on the heap or using free store manager, because this is a C++ program. As you recall, we discussed memory layout of a program loaded into computer memory, and there was a space for heap, space for C style dynamic memory allocation, and free store memory allocation. And here when the new operator is used, it will create brand new integer on the free store, and new operator returns a pointer. So ptr to int is obviously a pointer to an integer. So this pointer right here will be pointing to this brand new integer, which did not exist when the main function started to execute. So this is kind of rare situation with integers, but another example is that instead of creating a single integer, we want to allocate a block of 100 integers. So this is kind of more realistic. It's possible to attempt to do something like this. So we have this block of memory that we want to use to store 100 integers, right? So we have our integers allocated right here, and this new operator will allocate space for this many integers and will return back to this pointer the address of the first integer in this block. So these are examples of using new. So right here, let's try an example where maybe these strings were loading them from a file. So right now these are of course all hard-coded string literals, but potentially we could have an array of strings, and we want to decide at runtime how many strings we want. So there we would have to demonstrate this dynamic memory allocation, which is done with the new operator. We would have to declare it like this string. Okay, so this will be pointer to strings. Okay, and this pointer to strings will be initialized by new, and we say string, and we can say how many, right? So we can specify how many of these strings we want, and this is a variable, right? So we could define it like this size t. I don't know. We can create 1,000 of these strings if we want, or for example, if it is going to be used on a screen or in some kind of spreadsheet, we may know the dimensions of our screen or dimensions of our spreadsheet, and then decide how many strings we want. But so obviously we're not going to do much use of it, but you know, this will create 1000 strings dynamically at runtime, and this pointer will get access to the first one in this array. So right here then we could use our output to display. Again, I will just duplicate the code that we already used. Right here we can say, for instance, the first string in this array, I'll use just index 0 right here. So this is first string dynamically allocated, and use it in our output like this. So I'll just comment this out for clarity. Okay, if I build this and run it, you can see that still we're creating an array. This time we're creating an array of 1000 strings dynamically, and we get pointer to the first string in this dynamic array. And when we use index with this pointer, it gives us access to the first initial element in that array. And of course, because the default constructor is used in this case, the string of the length of the string is 0, and it contains this null terminating character, which is not really visible when we print it. What is even more important to know, rather than just the fact that we can allocate objects dynamically, is that it's a normal practice that when we allocate objects dynamically by the new operator, we have to destroy these objects by calling delete operator. So delete looks like this. Because this was an array of strings, we must use square brackets. Important not to forget square brackets. And provide the pointer to the first element. Now remember, we called this dynamic memory allocation in C++ a free store. So this free store has like a free store memory manager. And I'll try my best to give you a little diagram of it. So this is our program in memory, like this. Okay, so it allocates some space. Somewhere here we have space for dynamically allocated variables. And we can, right here, we're already allocating 1000 dynamic strings at runtime. So this area will be populated with array of objects, which are all strings, and they will be populated in here in this memory dynamically. Then we could allocate more things in this dynamic memory. It's possible. And so free store manager, which is automatically built into our executable part of our code by having this new statement used in our code. What it's going to do, it creates like mapping of all dynamically allocated chunks of memory, if you will. And it's not standard, but it's kind of standard practice that in front of every dynamic memory allocation, there is written the size of this memory block. So there's some kind of work, some additional work done to manage this heap memory in C++. So this memory management allows us to concatenate blocks if they're deallocated to, for instance, avoid memory fragmentation. But there is some effort behind this new, the way it's organizing things. And when we use this square bracket notation with delete, we tell this memory manager that please be sure to look at the size of this memory block in front of this pointer, because the pointer is pointing to the first element right here, the first element. This is where the pointer is pointing to. But the memory manager will be able to use square brackets to find out what is the size of this block and correctly deallocate this whole thing. And we'll say, oh, okay, this is no longer used, so the memory goes back to the system, and we can, next time we use new or, you know, any other way to manage this memory, this now becomes available. Now, if we forgot to use the square brackets, okay, and this pointer to strings was allocated dynamically, right? So pointer to strings was allocated with 1000 string objects, and it has this block of memory that contains a lot of string objects in this entire memory right here. And of course this is pointer to the first one. So if we tell our memory manager right here that we want to delete this pointer, it will go and attempt to deallocate only the first element of this block of memory. It will ignore an idea that if we do use square brackets in front of our pointer in the delete operator, it will try to use this, it'll find out in that case that there's not one but 1000 objects that were allocated, because this 1000 will be stored right here right in front of this block, and it will be able then to deallocate all of these objects, right? So this, doing it without the square brackets, is a big mistake, right? So this is really bad, okay? So this is bad idea. Compiler will not be able to give you a warning. This is our responsibility. This is why, by the way, we'd like to use dynamic arrays like standard library vector, which is doing all of this memory management at the low level very nicely for us. So for the most part, in perhaps 90% of code that you write, you'll never have to write new and delete on your own, because it's a tricky business, and there are lots of things that could be done wrong. So we just, here in this example, we just have to restore the square brackets to bring it back, because if this was allocated as dynamic array, we have to deallocate it also as dynamic array. I'm not going to require you to remember all of these details, but just remember that there's something about this delete. In fact, there's something about new and delete. There should always be match. Each new have to match its own delete, and this can be very challenging. Whereas, you know, new can be in this function and delete could be in 10 different other places, and this is complicated business, and at best should be avoided, because there are lots of ways to not to do this type of coding, but use standard library containers to create objects dynamically, which we will discuss later on in our presentations.